Hi everybody. So this is my first electronic stream, and what I want to do today is hook up my doorbell to MQTT and SIP. So what I have here is a Seidler loudspeaker and microphone module. And it's quite old, and back then they used some shitty proprietary protocol to interface with PBXs who supported that protocol. I hooked it up to SIP already, but the way I did it is I used the very old PBX. It's now like 18 years old, and hooked it up to an ISDN card in my SIP server, but PBX died down some time ago, and now I want to replace that whole setup with hooking this thing directly up to SIP. So what I'm going to do is basically replace all the electronics inside of here, and so that it's only a dumb microphone and loudspeaker. And what I have here is a Snome PH1, which is a SIP device, which is supposed for like public address systems and stuff like this. So plan is to either use this device or just go with a Raspberry Pi and a small USB sound card, which I accidentally misplaced, and let that do the work. Also, what I'm going to do is what I'm not going can now not show you is there's like a doorbell, actually bell thingy module outside, which is just basically two push buttons to contact closer switches, and those are going to be also hooked up to the system, but in a different way. So basically, what I want to do is to use either the Raspberry Pi GPIOs, or I have here a new ESP8266 board. It's just a generic China clone of the Node MCU boards. I don't know if you know the ESP8266 microcontrollers, but they are a really awesome device. They are basically a microcontroller with built-in Wi-Fi, and you can program them in C, or even they have even a Arduino core available. So if you're just new to stuff, you can really there's really not a big hurdle to get into that and program these devices. And what either it's going to do, either the ESP8266 or the Raspberry Pi via GPIO, is they are going to send me via MQTT. I will get into what MQTT is in a moment. A message which will then be processed by the rest of my systems. For example, I already written a quick client in Python, which enables you to what it does is it plays a sound on my computers and shows me a notification via libnotify. And yeah, that's basically my doorbell indicator on my PCs. But also it's going to be hooked up, like I have some audio systems here, which are based on a Raspberry Pi, and hooked up to speakers, and those are going to play various sounds, pretty nerdy sounds, like not just a ringing doorbell, but for example, I want to use like the sound from 2001, where it says, Hal, please open the pod bay doors, and Hal answering, sorry, I can't do that, Dave, and stuff like that. But before I can decide which way I will go, I basically have to open that device and look what's inside. If like depending on what's inside, going to go either with the Raspberry Pi version with the sound card, or with the GNOME PH1 version combined with the ESP8266 module, because the GNOME PH1 has an amplifier in it, so it can drive directly the speakers. So much for that. I'm going to wait a few more minutes before I start, so the more people have a chance to join, and then I will go into the rest. By the way, sorry for the background noise. I have a server here in the room, which I need to move back into the server room, which I didn't have the chance yet to do, so that's the noise you hear in the background. Sorry for that. Well, I think we've waited long enough, and now I'm going to start. So that's an Siedler TLM 611-0, and I already pulled up the schematics of it because we're lucky enough that they put up the schematics on their homepage. So here are the schematics. So the document is only available in German, but I will translate it. So it reads, the TLM/TK 611-0 is to be used on PBXs or Intercom systems, or the PVSet 322-0, which have a separated line for microphone and loudspeaker. Down here it reads, the loudspeaker has an looking for words. What's going on, brain? What the heck? Let's go on with the rest. I have a brain fart. Okay, the light switch may be loaded with 24 volts and 2 amps. The LED for the light switch can be powered with 9 volts DC. And the trimmer resistor can be used to control the volume of the microphone. So what we have here is basically there's just the speaker, which is directly connected to the clamps. The LED, which is all simply just LED, and then we have like this circuit here. What this circuit is a very basic single-ended audio amplifier. The trimmer here controls the gain, and as you see, it has only 2 wires, so it's powered by phantom power. What it means is that you couple in a DC voltage. I think it's 9 volts in the original system, and the audio signal of the microphone is then just modulated on that DC voltage. Basically, we maybe could use that. I have to look up the design specs of the Gnome PH1. What we can definitely try out is to just hook up for a quick try the loudspeaker to the Gnome PH1 output and see if that works. And before I'm going to do that, I'm quickly going to look up the specs of this Gnome PH1, and I'm going to pull them up so that we can have a look at the output. Have a look on the microphone input to see if that supports phantom power. By the way, just a quick show, so you know what, before we're going to continue, I'm just going to screw this case open and we're going to take a look inside. Let me get my tools. Yes, yes, I know. The ESD workplace is useless without a wristband, but my wristband broke down and I have to get a new one, so maybe with the next stream I'm going to do it properly and have a ESD wristband hooked up to myself. By the way, if you have any questions, feel free to just pop them into the chat. I'm going to try to answer them. Okay, I'm going to try to open this up further so I can show this to you better. Well, let's just do this way, and I'll take my webcam to show this to you a bit better. So, come on, focus. Well, sadly it's not going to get any better. I had to improvise a bit with the setup today. Going to work on it on the weekend, so it will get better in the next streams. So yeah, just a basic PCB here. You can see the speaker here underneath. Here is the switch for the light button, and here we've got the microphone. While I'm on it, I also can quickly show you the ESP board better, so you now can have a better look at it. That's the ESP8266 board, and you can get them quite cheaply online. Okay, going to unscrew it further. Also, next stream I'm going to hook up another camera which will give you a close-up, so you can watch better what I do when I do stuff like screwing, opening things and so on. So I'm now going to unscrew the PCB and hope that not everything falls apart. That's quite easily to be opened. So here we have the speaker, and here we have the rest. And actually, here's a second trimmer, which does not show up in the circuit diagram. Great. Well, we're going to take a look at that. and what the heck it's doing. Isn't it always lovely when circuit diagrams aren't correct? Wait, what? We have here a transistor 1, wait, let me show you that. Let me show you that. So, out of the way, cable. So here again we have the PCB, and you see there is in transistor 1 and transistor 3 and transistor 4 and 2 trimmers. Going to show you the diagram again. There's nowhere any word about a third transistor or the second trimmer, so yeah, that's fun. Maybe I go back to my original idea, and which was to replace the whole electronics, but yeah, let's see about that. So I just looked at the chat and there was a question what I'm modding. So what I'm modding is, I talked about it in the beginning of the stream. This is part of the door intercom system, and it's basically the speaker microphone part. It was originally designed to be used with PBX systems, which supported that analog interface, but the PBX it was hooked up to is 18 years old and it died down. So, and there's no easy way to hook something with that up to an SIP PBX. So I'm going to hook it up to either this device here, which was originally designed for public address systems, but it has a microphone input and you can use it as a door intercom system, or I'm going to hook it up to a Raspberry Pi with an USB sound card, and that in turn will then communicate with the SIP server. That's what that thing is. So let's just I lost where I was going to. Okay, what I'm going to do is, I most likely have to replace the microphone circuit because it is a two-wire interface, and it looks like the way it works is that the sound waves are modulated on the current that the circuit draws. So basically, I just noticed that I didn't switch to the camera, so I'm going back to the camera again. Sorry about that. So what I was talking about is this thing here, or like originally this thing here. This thing here originally is a door intercom device. Here you see the specs of it. And the rest I already said. So here you have the circuit diagram and the way that circuit most likely works. I'm not that good at analog electronics, but the way it looks like, what it does is it modulates the sound on the current that the circuit draws. What we can do is we can hook it up to my bench power supply and hook it up to my oscilloscope and have a look on what it does. I'll have to cherry rig a shunt resistor so that I can show you the current draw of it on the oscilloscope, but that shouldn't be a bigger problem. I think I have everything flying around here somewhere. So what I'm going to do is I'm going to quickly get the two scrap pieces of cable and then hook this up to the bench power supply and to the oscilloscope, and then we'll have a look. Actually, I plan on connecting my oscilloscope to my PC so that I can show you directly the screen of it, because it has an DVI output. But currently I don't have an DVI grabber card, and I can't interface it with my SDI grabber cards I use for the rest, because of the resolution it has. It puts out a DVI with 640 by 480, and I have to either find a DVI grabber card or a cheap scaler so that I can scale it up and hook it up to one of my SDI inputs or HDMI inputs. So let's get going here with hooking up the thing to the bench power supply. Just quickly going over to my scrap cable box to get some cables. Yeah, I even got the stuff to hook it up to the scope that we can see the current. That's an 5 ohm resistor with I think like 5 or 10 watts. I can't remember. I used it to make discharging curves of lithium batteries. So let's get cable tools out. So just now stripping up this cable a bit so that I can connect it here to the interface board and then hook it up to the bench power supply. Actually, this side a bit more. So going back to the circuit diagram, pin 11 is most certainly ground, and pin... You are fucking kidding me. I have to show you this. So this is the original camera. Well, I think you can read it. Yeah, I need to find a different solution for close-ups. So this thing here is the original connector, because this device here, let's get it out of the way a bit, this device here has like here an 10-pin post connector, and this hooks up to here, and that has like here this plastic thingies which connect to the back of the case outside the door, and then you just connect the cables. Oh, now it's sharp. And here the cables. But look at this here and remember the pins. We have 11 plus T2, T1, 12 and 9. If you look back over to the circuit diagram, we have T1, T2, 11, 14, 9, plus 12 and 13. So yeah, that doesn't add up. Which means we can't trust this document at all. So yeah, that's fun. So basically we can't even now hook it up because we don't... what I have to do now is reverse engineer the PCB and try to find out what's actually connected to where on this whole thing before I can continue with even hooking this up to an power supply and oscilloscope to discover how it exactly works. Oh, what joy. So yeah. Oh, I said I was wondering about the whole T1, 3 and 4 thingy. I just discovered T2, which interestingly enough, it's an SMD transistor. So do you see over here? That's most likely a transistor. So for some unknown reason, they mixed through-hole parts, like here the caps and the transistors and the potentiometers, with SMD parts, which does not really make sense. I mean, okay, you have to remember this thing here is 18 years old. Back then, there was still a lot of THT electronics production going on. Actually, I'm quite curious how they actually soldered that thing, because if you look at the solder joints, come on, camera, don't let me hanging here. Aww. Yeah, I definitely have to get something out of to show you the close-ups. Sorry about that. Oh no, here we are going. Okay, so if you look at the solder joints, and okay, to go one step back, for THT. Okay, THT means through-hole technology. Basically, it means like parts like this transistors here, who have like pins that go through the PCB and then are soldered on the back side. For commercial production lines, basically the way to go normally when you have THT parts is wave soldering. But the solder joints don't really look wave soldered. Also, you can also wave solder SMD parts. The way it works is you not only have the pick and place machine which places the SMD parts. Normal process from SMD assembly like today is basically you have the PCB and then you screen print the solder onto the PCB and then the pick and place machine places the parts. Which you've done before that thing was common, and if you have like wave soldering processes, what you did is you screen printed or with a machine with a machine placed drops of glue on the PCB, and you glued the parts to the PCB, and then you got the PCB into the wave soldering process, where basically a wave of liquid solder is washed over the PCB, and then everything is soldered. But actually, if you look at the solder joints, wave soldered solder joints look a certain way because of the nature of the wave that passes by. So basically they're not even. But this solder joints here look quite even. So I'm really curious how they actually soldered that thing back then. I can't really tell. But actually it's funny. This is a single layer PCB. You see, there's no copper nubs on this side. It's a single layer PCB. It's something you don't see today anymore. But that makes it actually fairly easy to reconstruct the circuit diagram. And actually, if you look closely here, this is a 0 ohm jumper resistor. So whoever designed this PCB was able to do it with only one 0 ohm jumper to cross another circuit. That's pretty awesome. Okay, back to the other camera. By the way, as this is the first time of me streaming something like that, I would really appreciate any feedback you have, so just drop it into the chat or into the comments. Like if I should not go into much, too much into the basics, or if I should go more into the basics, or if I'm jumping around or speaking too quickly, just stuff like that. Drop it into the comments or into the chat. So okay, to be honest, this sucks a bit that we now have to go through all of that to find out how actually connect this thing. Okay, I actually discovered one thing. There's the LED and the resistor for the LED. If you look at the diagram again, you see the line with the plus, and here's the LED and the resistor. So let's so okay, I'm going to cherry pick something that I can show you the PCB better. Let me see. Wait, I know what I'm going to do. Let's do it this way. I'm going to take a picture and put it into the streaming software so I can show you a real good close-up of the PCB. Let me get that cable. Oops. Let me get that cable out of the way. Okay. Let's get that over to my PC quickly. magic and get the picture over it again. Oh, it's working. Give it a moment. Okay, let's get the image pulled up here. Just a second more. So yeah, here we yeah, here we go. So here we have the PCB, and wait, it was actually a bad idea. So better. Here, now you can see what I'm pointing at. So here we have the PCB, and if you look closely, that here is the LED, which is here. So if you follow that trace, it goes here to the connector, and here's the LED, and then we have the resistor, which is here in the diagram, R8. We have here the resistor, and then it goes back to here. So the way it looks like is that here these two pins are connected. So what's here called plus is that plus pin, but if you remember, and I show it to you again, if you remember the connector of that thing, it has two pins with plus. So if you look back at the PCB, these two pins are here connected. So this are most likely the two plus pins. I will not later take out the multimeter and confirm that. But if we go from here, we have this trace here, which goes under the 0 ohm jumper and goes over to here. This pin is actually the transistor, which is labeled T3 on circuit diagram. And the pin it's connected to is most likely here the collector pin. So the transistor has 3 pins. collector, base, and emitter, and that's the collector pin. So basically, what it looks like that on this version of the PCB I have, pin 14 and does not exist, and it's actually 2 plus pins which are connected. Which would make sense because yeah, you have the same power supply supplying the LED and this circuit. Maybe apparently they like built it in a later version so that you can switch off the LEDs at day to save power, but back then that wasn't even a thing, and actually it was like new that this thing was even an LED, because all the other modules outside have like actually lamps in them, like tiny lamps, which run all the time, which is nuts. But well, maybe I can like modify that and hook up and relay to a GPIO pin of the ESP8266 or the Raspberry Pi to switch them off at day. It's just a waste of power. So yeah, so it seems like that's the case, and with that we have another pin which is called a pin 11, and from that we can just go and hook it up to the oscilloscope and look what's going on. So that's what I'm going to do now. Sorry for the delay, just need to do something for a sec. Let's do that. So, yeah, that's hooked up. Let's get some of those cables, whoops, for the power supply. Get those tools out of the way. Actually, this is really good that I did that streaming thing, because like in the first time for ages I cleared up my desk. And if I continue to do that streaming, which I want, that will motivate me to keep everything here in order, which is good. So, let's turn down the voltage first. So, just check again how I hooked everything up here. Plus pin is the wire with the red stroke, which actually is the positive side on the circuit diagram. Okay, need to let that show out a bit. So, okay. Let's get the oscilloscope probe. Just move everything clear up here a bit. So, first thing, I'm just going to hook it up directly. Oh, wait a second. I've unplugged the microphone. So, here we have the microphone. And can put that out of the way. Plug the microphone back into the PCB. Hook up the oscilloscope. And then configure the scope. So, okay, let's turn up the voltage. Oh, wait a second, the scope is in DC mode. Oh, no, it works. I'm going to show you the scope screen in a sec. I hope I can get it to get the connection to the scope working soon, so that I can actually show it you on the stream and the whole process of setting up the scope and everything. Let's wait a sec. Taking a look if I have something left that I can prop the webcam up so that it gives you a nice view of the scope. Just take can't take that. That can work. So let's hope that the cable is long enough. Yay, it is. And let's take a look. Huh. So that works. And let's do that. And here we go. Here you see the scope. Yeah. So what I did is, you see that the 0 setting for channel 1 is down here at -6 volts. The channel is configured to 2 volts per division, and I'm now turning up the power to 9 volts. As you now can see here in the readout, it says V1 is like the measurement marker. The 1 has a measurement of 9 volts, and you see the down on the left corner. You see like there's a small 1, which is the indicator for where the 0 position is of that channel. And now I'm going to connect the board of the loudspeaker system. It's now connected, and actually we don't really see anything going on. So as expected, most likely this whole thing is designed so it works by modifying the current it draws. So what I'm going to do now is unhook this again and put the shunt resistor in front of it, so that we can actually measure the current that's going into this PCB. I'm just unplugging the power. See, it's going dropping down back to 0. And then I'm just unscrewing here the plus line. Actually, no, I'm unscrewing the ground line. And then we're going to hook up here this cable, which goes into the shunt resistor. And then here we go. Then I'm going to hook up the positive side of the scope here, the negative side over here, back to the ground of the bench power supply, and then I'm going to plug it back in. Nothing exploded, so that's good. And now we can look at this scope again, and I'm going to turn up the gain of the scope. So now we have 100 millivolts per division, and what we see is, and we can do some math now, so that's a 5 ohm resistor. So if we have current of 1 amp, that would mean that we have a voltage drop of 5 ohms. Now we have a voltage drop of 250 millivolts roughly. Going to show you the scope a bit so that you can watch it better. So here you have the scope, and it's around 250 millivolts. And as you can see, it fluctuates. So if I clap my hands, did you see the spike going on there? That was my hand clapping. And if we now go, now I'm going to do some math. So yes, we have 250 millivolts, so 2.250. And if I divide that by the 5 ohms of the shunt resistor, I get a current of 50 milliamps. So this thing is drawing 50 milliamps currently, which is actually quite a bit. So basically what that means, at a voltage of 9 volts multiplied by 500 milliamps, this thing is like drawing 0.45 watts all the time, even if it's not in use. But anyway, what you can do now is to actually like see the output of the sound output of the microphone is. We can do what we can do is the scope is now actually in DC mode. So I can switch it over to AC mode, and now you see the it's dropping down to 0 because it's now AC coupled. And if I now am going to move it back to the center, come on, 0. Yay, 0. Actually, I hate that I don't have a button for that. That would makes things so much easier. I mean, it's a digital scope. You could just have added a button with one push to 0 the input, but whatever. Okay, it's now AC coupled. And I'm now going to turn up the resolution again. Now we have it at 20 millivolts, and you can see it shaking. I'm now going to turn up the time so we can actually see something going on here. And what I'm now going to do is I'm going to play a sine wave from my phone and put it next to the microphone, and then we should be able to pick up that sine wave on the scope. So now the phone is playing in 440 Hertz sine wave. Going to put the speaker next to the microphone. Trying to fix the trigger so we can get a better lock on the signal. Let's limit the bandwidth so it doesn't pick up too much high frequency noise. I'm interesting enough, it's really distorted. So let's go up for a frequency because it's quite low for... That looks better. So the phone is now set to a frequency of 2.092 kilohertz, and if we look at the scope readout, come on camera, why can't this stay focused? Damn it. Okay, I'm sorry that you can't read it, but it actually reads down here 2.09 hertz, kilohertz. I'm turning the the sound volume of the phone a bit down. So yeah, actually we now basically worked out that this PCB has a current mode transfer of the microphone input. And that's a thing PC sound cards don't really support. Neither this known PH1 doesn't support it. I'm going to turn the phone off now. Okay, better. Not so much noise. So I've either have to design a circuit, an amplifier circuit, which amplifies this current signal back to a voltage signal, a current voltage converter, which I then can hook up to an audio input, or I have to redesign this PCB for outside. I think the way I'm going to go is to design a small PCB which can go into the wiring closet, which will amplify this signal, the current signal, and to an audio level, to a line level audio signal, which I then can hook up to just a normal regular sound card. And actually, as the speaker is 50 ohms, it should be able to be driven directly from the sound card, because it's basically like in headphones. Could be that the signal is too low then, but that's a thing we can try out. So basically what I can do now is I have a few stereo jacks lying around here and a cable. I'm just going to solder cable to one of the jacks, and then we can hook it up to the speaker and just play around. And because if I actually hook it up to the Snow PH1, which has like terminals for speaker, I think I have to look it up, but I think the speaker output is too powerful. It should just blow the speaker out. I just read the comment about the noise. I'm sorry about the long, annoying sine wave sound. Next time I will just use the single shot feature and not annoy you so much with the noise. Sorry about that. As I said, I'm new to all of this, so that's basically just the things you learn on the go. Yeah. But to be honest, I think after soldering that cable on, that will it be for the first stream. I will stream basically the whole time I'm working on this project, so including the coding part and everything. And I will just now solder the cable onto some jacks, and then hook it up just to the Snow PH1 because it's already hooked up. And then just call it from from a phone here, and look what happens. Basically, just going to check something again about the speaker impedance, because just to be on the safe side, I don't want to blow the speaker. So let's look at the speaker thingy. checking the things. Okay, this NumPH1 is designed for a speaker with a specific resistance of 8 ohms or 150 ohms on the headset output. Yeah, the speaker we have isn't nowhere in that range, so that sucks a bit. So looks like it looks like we actually have to design a small speaker amplifier designed specially for that speaker, which it's not really that hard. But that's all going to be in the next stream. So yeah, I guess I'm going to close the stream for the day and just prepare a few stuff for the next stream. And glad that you watched. Hope you enjoyed it. And see you the next time. Bye.